Alright, so now we're going to jump to 2.7. 2.7 has to do with operations. Operations and composition of functions. So we're going to first deal with the idea of the operations of functions. By operations, it's just talking about adding, subtracting, multiplying, and dividing. And we're going to be doing operations to functions. We're going to be adding, subtracting, multiplying, dividing functions. Sort of where once upon a time you learn how to multiply, divide, subtract with variables, polynomials, powers, and all these things. But now we're going to apply it to functions. And the way we're going to do that, and at the same time, we're going to try to talk about their domain. Remember, the domain had to do with the set of all x coordinates. And the only time we really had to worry about a particular function in its domain was if you ever had a fraction. You did not want 0 in the denominator, so that was not good. And then when you had a square root, that's where you wanted to be careful, because remember, there's no negatives inside the square root, and you do not want to have a 0 in your denominator when it comes to a function. So those are the only ones that we have to watch out for. Now, the way it's going to work, this division, multiplication, subtraction, and addition, it's going to be like this. We're going to be looking at functions, and we're going to either add the two functions together. We're either going to subtract those functions together. We're going to multiply those functions together. Or we're going to divide those functions together. What this ends up being, again, this is just notation for notation's sake, but what ends up happening is just having f of x plus g of x, and or f of x minus g of x, and then we have f of x times g of x, and then we have f of x divided by g of x. All we're going to do is just either add, subtract, multiply, or divide them together, and at the same time be able to identify the domain. The only thing now is we have to, before we were just looking at the domain of one function, but now we have to satisfy the domain of both of these two functions. And then the fact that you're dividing them together, you're making a fraction. So when you're making that fraction, that means now you have to be careful where in this situation, you have to make sure that g of x cannot be equal to 0. So it wasn't, we don't know what g of x is, but whatever it is, once you divide it, ends up going in the denominator. So what that means is, now whatever that function is, it could be linear, quadratic, absolute value, it just cannot be 0 anymore. So we'd have to compare the domains of both of the functions to be able to come up with an overall function for the combination. So sometimes instead of saying operations on functions, they also like to call it algebra on functions or combination of functions. Use the same idea, but the main concept is adding, subtracting, multiplying, dividing. So let's get into an example. So I just want to just jump right into an example so we can see how these are done. So let's say we have, for example, let's let g of x be equal to 2x, and then we're going to have h of x equal to, what are we going to have it equal to? X squared minus 4x. And then we're going to have k of x equal to square root of x minus 1. And then we're going to go through these, be trying to add, subtract, multiply, and divide them in particular orders. So let's try our first one. Let's say, example A, we're going to have g minus h of x. And what this means, if I look at the notation here, it's just g of x. I'm going to subtract it with h of x. So when I do that, again, I'm replacing my entire g of x and my entire h of x. So I'm going to plug in whatever g of x is equal to right into where g of x was. So I'm saying g of x I know is equal to 2x, where h of x is equal to x squared minus 4x. So that means here I'm going to plug in 2x. On this side I'm going to plug in x squared minus 4x. Again, it's really important that you use those parentheses, because if you didn't use those parentheses, you wouldn't have noticed that you needed to distribute this negative to both of them. So what this simplifies to now, we're left with, use a different color, we're left with 2x minus x squared, but now a negative times a negative gives us positive 4x. And this I can simplify a little bit, because the 2x plus 4x gives me 6x. So this is going to be negative x squared plus 6x. And this is the operation of subtracting them. But now if I want to find the domain, I have to look at this function and think about, remember the only restrictions, so the domain is the set of all x coordinates. The only functions that have restrictions is the square root and a fraction. Square root, you don't want negatives inside the radical. Fractions, you don't want zero in your denominator. There is no value of x here that's going to cause a problem in this quadratic. You can plug in 0, you can plug in a negative, you can plug in decimals, you can plug irrational numbers. They're all perfectly fine. So when you're doing your domain, so again, you can write it in set notation. So set, remember set notation will be x such that x is all real numbers, because there is no number here that's going to make this function undefined. And if I used interval notation, again, I know that there's negative infinity to infinity when I'm identifying the domain, because there's no restrictions going on. If I had the square root, then I had to put some more thought into it. If I divided anything, then I have to put a little more thought into it. But there's no restrictions going on. So let's try another example. Maybe this next example will put a little more thought into what we do. So now let's say we're going to multiply g times k of x. Which that just means is I'm going to take g of x, and I'm going to multiply it. Sorry, not equals, multiply with k of x. Now, same thing as before, I'm going to replace the g and the k of x with parentheses, because I want to make sure I plug it in correctly. Because I know g of x is still 2x, so 2x is going to go here. But I know my k is the square root of x minus 1. Now, when we're simplifying this, there's nothing to distribute. I can't pull that x squared, that 2x in. So all you're left with is 2x times the square root of x minus 1. And that's it. It's not too bad. Just a combination or operations of functions. If you can combine like terms, you can. You have to distribute, you should. But there's nothing we can do here, because the square root is keeping it together. And so we just multiply it right outside. But now when I'm thinking about the domain, now, again, just like before, if I use set notation, I have to think about what is the set of all x coordinates here. Again, this x outside doesn't do anything. You can plug in a 0 there, just make everything 0. You can plug a negative, positives. Nothing happens to this 2x. But the square root, like I said at the beginning, is the only thing that has a restriction. And if you guys remember, the way we identified that restriction was taking what was inside that denominator. And then, because we know we want that radicand, not denominator, sorry, we want that radicand to be greater than or equal to 0, because all the numbers that are bigger than 0 are positives, which are okay inside of the square root. And then the square root of 0 is 0, which is a real number, making it a perfectly okay number to be part of your domain. So when I simplify this, that's just going to be x is going to be greater than or equal to 1. So that tells me that the values, all the values of x that satisfy this function are going to be those that are strictly greater than or equal to positive 1. So x such that, and in this case I don't have to say all real numbers because I already have this inequality telling me all the values that satisfy my domain. Now, when it comes to interval notation, all you have to remember is think about a number line when you graph these. The only reference point if you have is 1. Since there's an equal, that means I have a closed circle at 1. And then x has to be bigger than 1. And all the numbers that are bigger are always on the right. So when I write my interval notation, it starts from least to greatest. So I have 1 and then continues to infinity. Since I can include 1, that means I have a bracket around 1, but then I have parentheses, always parentheses around infinity. So, and this one involves a little bit more thought, but still not too bad when it comes to trying to combine them. Now, here's where it can get a little more difficult. And that's when I take k of x and I divide it with h. So that's going to look like, it's going to look like k of x divided by h of x. So this is the part where I said now you have to be careful, because when you're dividing, that h of x is in the denominator, meaning whatever function it is, it could just not be equal to 0. So again, I'm going to replace the numerator of k of x with the denominator, which is h of x. And I'm going to plug in whatever those two functions are, whatever they're equal to. Well, I know k of x is equal to the square root of x minus 1. And I know that h of x, h of x, I thought I mixed that up, is equal to x squared minus 4x. And there's not much you can do after that. Once you plug it in, it just simplifies to the square root of x minus 1 over x squared minus 4x. There's not much you can do to simplify this. You can't combine the radical inside of it. Sometimes you could simplify. Like how we saw in this example, we were able to simplify them, but that's not always the case. But now when I'm looking for my domain, I have to take a couple of things into account. One of them is that I have a radical in this problem. The fact that I have a radical, square root in particular, just like the previous example, I know square roots can have negatives inside. So just the numerator part I know is going to have to be strictly greater than 1 because I did that on the previous example. But now my other issue is, whenever I have a fraction, I have to make sure my denominator is not equal to 0, because those are the values that will make this function undefined. But to think of what squared minus 4 times that number is going to give you a 0, it's quicker to just take that entire denominator, because you want to know when that denominator, I'm going to put 4, sorry I wrote that wrong, is 0. You want to know when it is a 0. If you remember from math, the word is means equals. So x squared minus 4x, I want to know when x squared minus 4x is 0. Now I'm dealing with this small little quadratic equation, which don't forget, the first thing you always want to do when you have a power greater than 1 is move everything over to one side, which we have that already. But now I have to try to factor the left-hand side completely. So the first type of factoring we ever did was GCF. So I notice here, there's GCF of x, which will leave me with x minus 4 equal to 0. So I know here, x cannot be equal to 0, because if it is, then you're going to get it to be undefined. Or I have to set this x minus 4 equal to 0, which will give me x equal to positive 4. Which, again, it's equal to positive 4, but I know I don't want x to be positive 4, because then that is going to make this function undefined. But now I have 3 different ideas to think about. Let's say if I'm staring at a number. Oops, sorry about that. Let's say if I'm looking at a number line. Well, I know that, here I'm going to do this in 2 colors. Let me get this brown and this orange. So I know for this inequality here, then a number I have to reference is 1. And I know that 1 is equal to, because it has the equal to part, and it has to be everything bigger than, oh, sorry, I keep dropping the markers. It makes this large bang. Now, not only do this satisfies the square root, but then these I have to take into account, because at 0, I have an open circle. And at 4, so 1, that's 2, 3, 4, I'm also going to have a closed circle. Maybe I should do that down here. I'm having an open circle, an open circle. But then everything else is perfectly fine. Those are the only 2 places that have an issue. Everywhere else, everything is perfectly fine. So that means everything in between, everything above, and everything below. But the problem is these 2 have to coexist with each other. So if this one is saying that it has to be bigger than 1, that means I'm not even going to consider any of these values. Even though these below 1 is perfectly okay with the denominator, it's not okay with the numerator. So that means you're actually going to get rid of all of these, because the only thing you want is where they overlap each other. So they overlap each other from 1 all the way up to 4, because even though if you plug in 4 in the numerator, it's fine, you can't plug in the denominator. So we're going to have to cancel that one out as well. And then we have to start again and then go to infinity. So what ends up happening is my solution are these 2 portions of this interval. So what that means, when you're writing your domain, let's say if you write it in interval notation, let's see if I can squeeze this in here somehow. So domain, I'm going to put I for interval notation. It starts at 1. I'm going to write it up here. Starts at 1. Stops at 4, and then starts again at 4, and then continues to positive infinity. But 1 is perfectly okay with the k of x and h of x. Perfectly fine. There's no problems here. So with this 1. So that means everything starts at 1 but ends at 4. But since 1 is perfectly okay, there's a bracket around 4. But then now brackets around 1 and then parentheses around 4. And don't forget to put that union there that tells us that this is one complete function together. But the main thing to take out of this is that whenever you see, when you're doing the domain, is whenever they are overlapping each other. You want to watch out for that. Make sure you're looking for that. Here's another example of when you can either subtract, multiply, or divide, or maybe you want to do it all together. And this is a very important part, especially if you're going to continue with mathematics. This is going to be an important issue when you get into calculus. And that is the difference quotient. The different quotient looks like this. When you're doing it, it is f of x plus h minus f of x over h. So this is our difference quotient. It helps us a lot with slopes of tangent lines that you're eventually going to look at someday. But if you notice, what's happening here is that there's an evaluation, which we did this last time, how you can evaluate a function. It doesn't have to be with numbers. Sometimes it could be with letters. And then if you notice here, it's asking us to subtract f of x. Okay, we don't know what that is yet, but once we do, we're going to subtract that from the evaluation of x plus h. So without further ado, find difference quotient. I'm going to put dq for, I'm going to put f of x equal to 3x minus 5. So this part, I already know. I can already plug it into my f of x of the formula. But before I do that, I want to be able to find that f of x plus h, because that's probably the most tedious part of doing the difference quotient, is the x plus h, especially if there's a bigger polynomial mixed in. So what I want to do first, I want to do f of x plus h equal to 3x plus h minus 5, excuse me. Because instead of plugging f of x, I'm going to put x plus h. And I'm going to plug that everywhere there was an x. So luckily there's only an x in this in this f of x. So once I do that, this is going to simplify to 3x minus 3h minus 5, if I'm not mistaken. And then I already know what f of x is. So all I'm going to do now is combine them all together. So what I mean by that is, here's my f of x plus h. So again, this used to be that. And it's equal to, 3 times x plus h. I wrote it in a different color, minus 5. So I want to be able to plug that in. Hold on. Let me scratch that. That's going to be 3 times whatever's going to get plugged into that f minus 5. And what's going to happen is I'm going to plug in x plus h and then x plus h here. And then, so if we notice, we already have the f of x plus h. I know what f of x is, so I can do this all at once. I can do f, so this is my f of x plus h. So it's going to be f of x plus h minus f of x all over h. So when I plug this in, so I'm actually plugging it in up here. Let me bring it all up top. So we're starting fresh. So let me just bring this up here. So when I plug in this f of x plus h, this is what I'm plugging in right here. Because it's 3x minus 3h minus 5. Then minus what f of x is. F of x is 3x minus 5. And again, I'm using parentheses because this negative is going to distribute over h. Which then this I can simplify a little bit. Because I'm going to have 3x minus 3h minus 5. And once I distribute this negative, that's going to give me negative 3x plus 5 all over h. And then here, my 3x's cancel, my 5's cancel, and I'm left with just negative 3h over h. Which I'm left with something I noticed. I made a mistake. This is supposed to be positive here. So that means that that's positive, means that's positive, means this one's positive. And I made a mistake because it's 3x minus 5, and I had to distribute this 3 here to this x plus h. So it should have been 3x plus 3h, not minus. So the h is simplified, and my overall answer is 3. So I'm not finding no domain here. Things simplify. That's all I'm doing to these, combining them, not trying to find a domain. So let me close this off here. And let's try to do this to another example. Let's say we have, let's do something a little bit bigger. It's going to be a little more tedious, but it should be good. I'm going to say f of x is equal to, I'm going to write it down here just because there's no room. I'm going to put negative 2x squared plus 4x minus 1. So I'm trying to find the difference quotient, but it's probably important that I try to find the f of x plus h first. What I mean by that is I should find this part here, the x plus h, because trying to do this all in one problem, if I didn't have this f of x plus h, doing it all in one shot is going to make it confusing and cluttered and difficult to find the answer. So now here I'm going to substitute all my x's with x plus h. But before I do that, I'm going to replace them with parentheses first. 4 times x plus h minus 1. And everywhere I had an x, I'm plugging in x plus h, x plus h. Now, you just have to be careful with this portion here, because that means don't distribute that power. What this x plus h squared means, it means x plus h times x plus h, which will give you x squared plus 2xh plus h squared. So when I plug that back in, now if I bring this back here, it's going to be negative 2 times this entire thing here, x squared plus 2xh plus h squared. And then here all I have to do is distribute my 4, which will leave me with 4x plus 4h. And don't forget about this negative 1. Sorry, I squeezed it in there. I'll give myself more room on this second one. Now I have to distribute this negative all the way through, this negative 2. And don't forget, all this is, I'm just doing the f of x plus h part. I haven't actually did the whole entire difference quotient. That's why it's important to do this portion first, to not cause any confusion. So now, we see here, we have, and once I distribute, it'll be negative 2x squared minus 4xh, and it's going to be minus h squared plus 4x plus 4h minus 1. And that's just, this whole thing here is just the f of x plus h part. I'm going to then subtract that by f of x, and then I'm going to divide it by h, all in one. But I'm going to do it on a separate sheet of paper. I ran out of room, and I don't want to just cram everything in there. So here it is. So I'm gonna do it next to this one so it doesn't get lost. I don't have to be pulling it back. So I'm gonna plug this entire f of x plus h here first. So let me bring this up here. So it's gonna be negative 2x squared minus 4xh minus h squared plus 4x plus 4h minus 1. Again, and this is just the f of x part. I then need to subtract by, so again, I'm doing the parentheses because I need to plug in f of x. And it's really important because you're always, if there's more than one term for that f of x, you're always going to have to distribute that negative. It's always important. Again, if you want, you can even put in the f of x plus h in parentheses. So that's going to leave me with f of x is this entire part. Here, I partially given myself more room. It's going to be negative 2x squared plus 4x minus 1. And don't forget, this is still all over h. So then this is going to simplify to negative 2x squared minus 4xh minus h squared plus 4x plus 4h minus 1. We have to distribute this negative through, which is going to give me plus 2x squared minus 4x plus 1 all over h. Now, just like the last one, I have to see if anything cancels out or if I can simplify anything. So right away, I notice that the x squareds can cancel. I also see that I have the 4x that can cancel. I also see that my negative 1 could cancel. These are all things I can cancel out. So then that would leave me with now just with negative 4xh minus h squared plus 4h all over h. And something I can do here, so again, I've done all this. I'm going to remove this one now so we can center this up. What I'm going to do now is you should, whenever you're dealing with fractions, a golden rule is that you should probably always try to simplify if you can. So the way I'm going to do that is I see that each one of these contain an h. So I'm going to factor out the h from each single one, leaving me with h times negative 4x minus h plus 4 all over h. Here, I can simplify my h, leaving me with negative 4x minus h plus 4. And that will be my solution for the difference quotient. Again, if you want to write what the domain of this is, you can. There's only one x here. Again, we don't know what h is. We can assume it's some constant. But there is no restriction on a 4x. So this domain would be all real numbers from negative infinity to infinity. So these are things that you can do with functions. The evaluation part, that came from a previous section when we first introduced what a function was. When we talked about the definition of a function, vertical line test, and then we talked about how we can evaluate functions. And that's what I did here. We were mainly evaluating with numbers before, but we also did some examples when we evaluated with letters. So that was an example of it. And this is putting the idea of evaluation with the operations on functions, or the algebra of functions, or some people call it the combination of functions, which means you add, subtract, multiply, or divide them. So I'm gonna end this video here. Again, we're not done with 2.8, but I think that's a long enough video. And on the next video, I want to talk about what it means to do composition of functions. And that's gonna be on a separate video. Okay, thank you.